Hello, everyone, and welcome to today's webinar on transformer circuit impedance, stray losses, and magnetic balance. My name is Sausan Adnan, and I'm the marketing manager for Megger Middle East, and I'll be hosting this session today. Speaker for today's session is Mr. Ja'far Al-Darazi, who's an area sales manager for Megger Middle East. Before handing over the mic to Mr. Ja'far, I would like to highlight a few points. You will be all muted to avoid any disturbance during the presentation. You can submit any questions at any time during the presentation by typing in the box, and I'll be reading the question out loud during the Q&A session at the end of the webinar. You can also follow our social media accounts, which I will paste in the chat box to get latest updates on events, webinars, and so on. All recordings and presentations will be shared within the next 2 days of this event. And please register for our upcoming webinars. I'll paste the link as well in the chat box. So I'll be handing over the mic to Mr. Ja'far. Mr. Ja'far.
Thank you, Sausan. And it's a pleasure to be with you here today, operating from Bahrain. And let's start our session for today. This is me, Jafar Al-Darazi. I'm, as Sausan say, area sales manager, as well I'm doing application job, where I very much specialize on transformer testing. Since 2013, I'm doing this. And as I said, I'm operating from Bahrain, from the Megger Middle East office. So our agenda for today, we will speak about short circuit impedance, and then followed by the most focused topic today, which is frequency response of stray losses. We will define this. We will see also from standards what's mentioned about and how to operate it using the tracks later in the live session. And we have very few slides talking also about the magnetic balance and how to operate it on power transformers. Starting from C-grade brochure 445, as a detectable failures, we are looking for deformation of the winding. So whenever we have suspected our power transformer to have some deformation, we have some indications will lead us to do this type of testing, the short circuit impedance. If we have high on-rush currents, high through current faults, Buchholz relay main tripping, or even protective relay tripping. Sometimes some topics will lead you to starting about short circuit impedance. The way you do, it's explained here in the C-grade brochure. There is also some reference which is asking you to consider it as a fingerprint, and you repeat this every time for making sure there is no change with the new winding. This method, it is mentioned here using an AC source, preferable with variable frequency source. And this means actually the frequency response of stray losses, but only single frequency, which is the power frequency, will be considered as a short circuit impedance. And in our region, or almost all the planet, either 50 hertz, the majority, or 60 hertz in some countries. So doing this short circuit on the low voltage side while applying voltage on the high side or injecting current even, you will lead you to measure the impedance of the power transformer, and then you will apply some equation to finalize your three-phase percentage impedance, giving you the final result you are looking for. And as an interpretation for the result, you should have no difference more than 2% compared to the factory test report. If you start having difference and it's higher than 1%, then it's good to investigate more and run more tests. Another indication, the short circuit impedance itself is an indication for doing FRA, which is frequency response analysis, or another fingerprint result test as well. Just if you have doubts or if you have exceed the acceptable limitations. There is, of course, some difficulties. It is not mentioned here in the IEC or CGRE about how thick your short circuit should be on the, how thick is your cable that doing short on the low voltage side. Some people may put very thin cables. We realize this from the real experience from the field that we recommend people to get very, very thick cables doing these shorts because you have very high current on the low side. So as a short circuit impedance, we have equivalent circuit, very much known equivalent circuit of power transformers. We have high voltage side and low voltage side, resistance, inductances, and ratio in between. What we do is we put a very thick short on the low voltage side, and we start applying voltage from the HV or injecting current. Injecting current would be more smart. We Meager today are offering the inject method more with our new trucks facility. This will allow us to run the test at a very, very minimum power consumption, as well not needed for a very high three-phase source, like what used to be people doing in the real field and even in the factories. Therefore, we have equation from IEEE. We are applying this, giving us the percentage impedance three-phase. It is already proven by standard, and it is just actually a basic physics that is driving and proving this formula for us to be used. And it is part of the software. You don't do it. I mean, if you run the test itself from Meager unit, it is already automatically inbuilt. You just do it phase by phase, and automatically will be calculated for you. So as a short circuit for the low voltage side, we say we measure impedance per phase from the HV side. So we need to switch between the phases. And then we calculate it using the previous formula I show. And then we compare with the nameplate mentioned value. Normally it's a percentage Z or percentage voltage impedance. There's different name, but it all the same meaning. You will usually find this value written on the nameplate of the power transformer where you can compare. Of course, if you are at the factory, you are doing this to put it on the power transformer. Of course, you can also compare between the single phase measurement between the three phases. So using the tracks, I'm providing quick example here. So we will be using, if I can highlight the green point here to start injecting current to H1 phase here, and the return will be to our source. This is a current source. We inject little current to the power transformer while we are putting extra leads on the low voltage side, making the short. And then you have a voltage tunnel here, which can measure the voltage. You can measure the voltage across it from the point here, but it's good to have like 4-wire method and you measure the voltage separately. Then you can get this per phase. For example, here 1UW, it's written here as an IEC, while here the connection actually is showing ANSI or American Standard. So it's the same, but just different standard between the result showed here and the connection. So UW, which is this part, and VU and the WV, the three-phase result here. We have the Z, and from the current here, from the voltage, from the formula I showed before, we could calculate what we call it measured impedance here. We compare it with what's written on the tab impedance in the factory that have been done before. And we could see like 0.82, which is less than 2%, between the measured impedance and the tap impedance, which is good as C gray telling that this has to be less than 2, and we are good at that. And even the XS variation, which is this one, we have very, very low also variation. This measured impedance is going to be the same always, unless you start having more shorted turns within your transformer that can even be proven by ratio test, but this is another way of seeing it. Also, as I said, in a deformation of the winding, that is also a good point to detect if you have or not. Moving forward to our most focused topic today, which is frequency response of stray losses. It is exactly the same as short circuit, and from the definition here, it is only a source with a variable frequency. But before that, we need to go to the detectable failures. We start seeing more things here. We can do like a detectable failure, local overheating due to excessive ED current losses. So if you have ED current losses, this will always generate heat within the core or winding, which is something by insulation testing, you maybe try to do it when you start seeing your transformer is getting overheated. You maybe test the insulation, you feel there is some leakages, but maybe it's all good. So you start thinking about having more ED current losses within this transformer. Then you would need to check this test, frequency response of stray losses. I have very good explanation slides where I will go through it in the next slides, showing what is this exactly and why it is showing ED current losses. And also, if you have stray flux, that will also telling you after finding the results of this test, what it should be and what it should look like, and what is even the acceptable here percentage from the delta of inductance or of delta of the resistance. We will focus more on the resistance. Delta resistance, it's strange to mention that resistance should always be the same at any frequency, but let's see what is happening. So as I said, it is same measurement as short circuit impedance, but we will perform this starting from 20 hertz till 500 hertz. This is the normal band we are working at. Sometimes 500 hertz will have very high voltage. Due to the some limitation, you maybe reduce it or maybe reduce the current. When you start experiencing this, you will figure out why we are doing. And later in the example, you will see this clearly. We will focus on the resistance as a result of this test of frequency. So we will look to the relation between resistance and the frequency. Also, we can look at it as impedance with the line frequency. It is diagnostics here. I mean, the diagnostic depends on information that is easiest to see at the higher frequency, which is 500. So we will focus more on the 500 hertz. It is just because we can see big difference in the higher frequencies, and we can define the skin effect and the eddy current loss also behind this frequency more easy than 50 hertz or even 100 hertz. So this will detect us in reality that the short circuit between parallel strand of the winding, what we call it axial displacement of the winding. And I have maybe some slide trying to explain what we mean by a parallel strand as well. So this is my short circuit, which is I showed earlier. We will focus that we will measure this resistor part while we are putting short here, but we will change the frequency. Now I will define what we call it a resistance of DC resistance. If we inject 0 hertz, that is just like doing winding resistance. the winding resistance will be likely a fixed value. But if you start putting AC current and you start measuring the resistor part, you will see some increase of this resistance. And this is due to the skin effect. The more frequency you have, the more resistance you will face. That's exactly in reality. If you have harmonics, it will always generate heat, even though you have only one conductor or one joint. At 50 hertz, you see no heat generated at 50 hertz, but with the higher frequencies, you start seeing some heat. And this because of the skin effect, because when we say harmonic, we mean that we are operating at higher frequency because the system needs to generate some harmonic due to some maybe motor operation or even some loads that will require high frequency currents. This high frequency currents will pass by the windings or any even conductor, which is usually it's dependent on it's a cross section area. The more frequency you go with this current, you will face higher resistance due to the skin effect. And I have example here, maybe in the next slides. But before that, we are talking now about ED losses that might occur, which is refer, as I say, to the skin effect or proximity effect, and also the structural component of the transformer, where also the core and in non-illuminated direction, this will all cause ED current losses. I will show then in the next slides what I was telling about the skin effect. But before that, the self-inductance eddy current, we have designed our transformer to have eliminations which can reduce the eddy current, and we are insulating between these two, between each plate here. So we have less and less eddy current, we have better flux moving, but if we have it all one piece, it will have a huge current, will increase in the reluctance. For that purpose, we design our transformer today with this way of design that will reduce the eddy current. But if we start losing this little insulation, because the transformer start losing this insulation, this will maybe generate more eddy current in this part, which will add heat to the power transformer. And the way to detect it is doing this FRSL. When you generate at higher frequency, this will appear more clear, more obvious for our testing. When I start talking about DC resistance, I should show this circle, which is just likely the current will be distributed across the whole section area, flow through the conductor. But when we start having an AC, we will see the current more on the sides, which is likely what we call it a skin effect. And this skin effect will be even dependent with the frequency. The more frequency we have, it will be less and less area for flow of the currents, which is just like a higher resistance in reality. So with the nominal frequency, we have like more area, more cross-section area that the current will flow through the winding conductors. The higher frequency, it will be less. And this will cause even more and more less when you start having issues like short strands or more short within the lamination within the core in both regions. So this is a good test as a frequency response of stray losses to detect us for what we call it as stray losses is just like we see the higher losses within bad, let's say, designs or things change from good to bad in conductor or in cores itself. And as C. Gray mentioned, we have to maintain 15% of the resistance delta change between now and maybe previous result, or maybe in the future if we compare it with the current result. It's not really added much of time for the total testing time. It's very fast testing. it will not really spend even more than 15 or 20 minutes to complete this test across multiple tabs even. And this is, as I said from the beginning, we are looking for a very specific faulted, shorted strands. And this is the connection, just like the previous short circuit test, where we have short on the low side, and we are connecting between phase 1 to phase 3. This is only for the first phase, but for all other phases, we would need to repeat the connection here and do it, which I will show in the next minutes, how to run this lively on a real power transformer and measure it with you together, and then I will have your question as well. Magnetic balance, I will be explaining this by doing the connection and explaining what we are doing. So at magnetic balance, we are applying on the UV phase with some voltage. It's at the time, for time being, we are only pre-selected voltage with our testers, where we can put some voltage here, for example, between U and V, but we have to measure across the 3 phases separately. We are only applying on one phase, and we are measuring across the 3 phases. We repeat the same thing for the next phase. We apply from VW, so we will put the hot volt lead on the mid phase. We take the return from the W, and we measure across the 3 phases from the analog channel for our measurement. So this is our voltage source. Previously in the short circuit and FRSL, we were doing current injection from here, but it is the same source that we are also using here as a voltage source. And we are measuring the voltage across each phase here. And last phase will be also the same. We apply from last and we take the return from the first. We measure across the first 3 voltage channels, channel 1 and 2, 3. It's already programmed if you select the magnetic balance test. And this basically will allow me to detect any issue with the distribution of the voltage within the flux circuit, which is the core. If it's not demagnetized or it is well demagnetized, this kind of issue we can see. And as a magnetic voltage, we induce phase voltage, just like other 2-phase voltages as well. So as an example here, we have a table. If we apply from first phase, we put 100% voltage on the first phase, we get here likely 68, and here maybe 31, which is the sum of these two will be equal to 100 or close. We accept still some percentage. At the moment, there is no clear study from the standards for it to put acceptance criteria. There is many people talks about different way of doing it, different acceptance criteria of a percentage difference, but there is no clear understanding within standard papers. At least I haven't passed through any, but what we are trying to show here that the flux will be distributed to the near leg, which is if we apply from the first phase, we could see higher percentage on the mid leg, and the far leg will have less. And if we repeat this on the last phase here, if I take the 100%, we get around 68, which is copied from here, and the 31 would be reflected to the far phase. But if we apply in the mid phase, I would have same percentage on the shoulder or on the sides, like we apply on the mid leg, but we get 50% here and 50% here, which is just like you do it from the middle part. And the flux will be distributed equally across the 2 side legs. So that's it for the magnetic balance. This is few slides, I know, but now we will talk very much in depth on how to do it and seeing it lively using the tracks from Megar. It's a multifunctional, which we can utilize it and do all of the tests I have mentioned. I'll be running the test now. If you have any question for the theoretical part, you can just now type it, but we will handle it later after the video. We might have some some issue within the sound during the presenting, the live presenting. I would like ask you to, if you can just raise your headsets or your speakers to hear well. We are sorry for that, but you can see it at least in reality. But we will share this again with you where you can see it much better later. Hello. We will demonstrate three tests: short circuit impedance, frequency response of stray losses, and magnetic balance. Using the tracks from here, tracks 280, I'll be operating from the screen, and I will make my test setup with the power transformer I have here. I will start from the screen, going and defining the test by showing the test connections, and I will do it. So let's start here. I will go for new. I will be selecting these three tests as short circuit impedance, frequency response of stray losses, magnetic balance. I'll click OK. So I have these three tests in my track, which is favorite based because I will only focus on these three tests. This is manual control, which is we will not use it, but it's always available. So let's start now with short circuit impedance. By entering this page, you have to fill a picture group of your transformer. I need to show my nameplate for my transformer. So this is my nameplate. It is clearly DY11, 11 to 415 ohm. So I will be entering these details plus 25 kVA power rating for my software here. So I have DY11. It's already entered. I can just click show you. I can just type it, click accept. It's just the same. I can enter my power 0.025 MVA, which is reflecting kVA. It is the same for secondary. For some transformer has secondary MVA output is different from primary, usually with tertiary. My taps on primary side, correct. Tap changer is the energized tap changer, which is correct. I have 7 taps, and I'm testing the tab number 4. I can show you later on my power transfer. I have 3 phases to test. I just need to enter the tap voltage, which is 11 kV, the nominal of my power transformer. Tap power is 25 kVA, but it's in VA. My tap impedance is 3.71. I can accept. Now I'm ready for the test. I just need to know what current I am injecting. I am injecting at 0.1 amps, which is sufficient for this test. And you will know later why I'm using very low current. It is also helpful. You can do the test with a very low current. I have here the question mark where I can click. and show you the connection. So I need only two cables, which is Kelvin lead, connected to my bushings. And I have two wires going, two to my channel one black, one red. And the same cables, the red will be also connected to the green output here, which is current injection channel. So now I will do these connections. So on my tracks, I have P measure, which is from my Kelvin lead, and I have also the same leads here connected as a source output, which is I have two leads as a Kelvin, red and black, and it's each ending with two wires. So one to my measurement channel, one to my source channel. And on my power transformer, I have only two wires, one connected to the middle phase and one connected to first phase. I just need to apply the short. So I'll be using a shorting lead. This needs to be tied very well so I can ensure I have proper flow for the current between the three phases while I'm injecting some current between the two phases. I will be switching these two clamps to the next phase and to the third phase one by one, and I will do it with you together. We go now to the software. So in my software here, I'll click OK. I confirm my connections. I have the interrupt. I can release it, and I have green play button to run the test, which I'm ready after filling all the details here. I will just inject my current and wait for my measurement. So I finished the first phase. Now I'm moving to the next phase, which is doing this connection. I will just take these two wires, switching them to the next phase, which is between V and W according to my disconnection diagram here on the tracks 16. I'll click OK, and I will just click play again. So for the same current, it will be injected on the second phase, and I'll be waiting my result to appear. Yes. Now we move to the third. So just going to the last phase. Let's make sure it's quite well. So on my cards, I can just click again question mark and show you now we are connecting between W to U phase. And I'll click OK. I confirm this connection. I will start injecting. So now my third phase show up, and now we could calculate the measured impedance for the three phase, which is almost same as 3.7. And I can go back to the nameplate, which is showing here 3.71, also mentioned on my nameplate. So this test is to confirm this result, just like what's been done at factory and mentioned here. And this should be within 2% according to international standards to be accepted or not. So this is the first test, the short circuit impedance test, done in around 5 to 6 minutes. Now we will move to the next test. But before that, I would like just to save this, so I will click save. It will ask me if you want to give it a name. I will click here. I click as a demo to be saved with the date mentioned and time mentioned. I click accept,
Now click OK. So I saved it in the internal memory of the drafts. I can show this result by going to the report page. I have some details of my power transformer. If I go up, I have more details even to be entered. I can do this part later in the office. If I scroll down, I can see my short circuit result. I can go to the disk by clicking this icon, and I can run it again maybe, or copy it, paste it again, or delete it, or export only this part, or you have the total export icon, or to even export it as a text file. So I'm done with this disk. I have shown its result. I can just go back to the application by clicking here. And as I said in the beginning, I'm running short circuit, and then I will move to frequency response of stray losses. I will go there. This is having exactly same connection as the previous disk, which is the short circuit. I already copied, or the system copied the vector group from previous disks. It's also copied all other parameters that I don't need to re-enter. I have here 0.1 amps. I said in the beginning that I will explain why I'm using very low current, because it does the job for me. I don't need to go for higher current. For this disk, I will again reduce it even more. I will put 0.05, which is 50 milliamps, even half the current I have used in the short circuit convenience. I will explain why during the test itself. I will just need to scroll down here and show you that it is highlighted here, injecting that amount of current at 20 Hz for the first phase, and here increase the frequency until 500 Hz. So frequency response of stray losses will address for me any issues related to the sound of the terms of my power transformer. That's why we go and change the frequency, looking if we have increase in eddy current within our code. The example I have here is not a disk, as it is distribution power transformer, very small rating, but it's good just to implement this disk app. I will be taking question mark to show you the connection. We have the short among the three phases without the neutral, and we have almost the same connection as the previous one. I will go to my test setup, and I was finishing between WU. I would like just to start again, so I will go and connect UV again, so I can start from the beginning. I will go to software now. I will click OK, and I'm ready for the test. I will just click play, so I can start injecting the current. And we can see the signaling here. It will update the result for each frequency, and you can see what frequency we are running at. You can see the two analog, ammeter and voltmeter, and you can see the result here in the graph. Also, we have the graph icon. We look at the graph will be built up. We can show this later on in the report as well. So we are now at 500 Hz. I said I will explain during the test. I was injecting 50 milliamps. I was having 21 volt at frequency 70. If I go even less frequency, I have even less and less voltage. As long we increase with the frequency here, up to 500 Hz, we see there is a rise in the voltage. So if I choose 100 milliamps, this may exceed my voltage limitation output from my track. So for that purpose, I was system at a very low current. It's not something you have to fix it at higher current. It's just a matter of power you are sending to your test object, which is the transformer here. I am sufficient with 50 milliamps to show the full graph details, which is this graphical representative between resistor and frequency, where I need to compare every time I measure. Maybe this year, maybe after some years when I start comparing with the previous result, or maybe from the previous years I can also compare and see if there is increase in the resistance at higher frequency. I know by physics it's not very much valid, but in fact it is valid when you increase the frequency over coils that you will have higher inductance. It's just like getting an open circuit. It is just like blocking higher frequencies as well, has different understanding. But we aim here to show that we provide this graphical data that you can compare every time you measure with the previous time. And you can show you have no change in this result. So I click OK. I have two more phases to run the test at. So the next phase will have just like the second phase. So I will go to my test setup. I'll be switching just the two wire to the next two phases. And I will go to my signal now and click OK for the disconnection. I confirm. I can just click run again and run the test again. I should see identical result between the phases. So I will look also to the graphical data showing that the results are the same. So testing now, taking some time, 20 hertz, and keep rising the frequency. Now we are at 200 hertz, 300 hertz. And you can see the voltage on the left side, it is getting increased 29 to 55 to 83, and now 113 volt at 400 hertz. At 500 hertz, it's around 143 volts across it. I will just click the graph icon. So you can see the two graphical data are on top of each other almost. We have slightly increase on the first phase. Now let's run the third phase, which is I can just click OK and click the question mark, which is already highlighting third phase. I will go to my test setup. I will be switching this from W to U. If you switch between the two, there will be no polarity issues because we are injecting AC here. But I will just go and run the test with the correct connection. I click OK. I will run the test and wait for the result. We can see repeated result on 20 Hz, 40 Hz, 50 Hz almost as a drop voltage. And we will wait till then to put the three phases comparison. So it's over now. We will go to graph icon, and we can see now we have the two phases on the sides are almost identical. The mid phase is having a little bit less resistance at a very high frequency. Maybe that's normal phenomenon for this transformer. We record this and keep it in our reference for the future use, and we always compare with this result. We can click just OK. We save the result now, so we save it, which is important part. We can later export it as a PDF report. But now we are done from the second test, and we can move to the third test. I will go to report icon just to show you how we are reporting. We will gather the two reports. I'll be waiting until it's finished loading. I go up, so I have here the test result for short circuit, and this test result for frequency response of stray losses. If I go down more, I have the full picture also with the graphical result. I will go to the application, starting my third test, which is magnetic balance. For magnetic balance, I will be changing lots of connection. I will be showing all the details on my setting and test setup. So I'll just go to magnetic balance. In the magnetic balance, first you need to enter the victory group, which is already copied from previous test. I can select any voltage from here. I will select only 125 volt. And I can see there is a three rows for my test. I can see that apply test voltage that I have used, I will be applying on UV, and then I will measure it on UV, which is the same, and then I will measure it on VW, and then I will measure it on the value at the same test label. Then when I move to the second, I will just apply on the second phase, and I will measure on the three phases. And the same for the third phase apply, and I will measure the three phases. I will put all the results here. Or the system will put all the results here. So first I will start with the test connection. So I have bit, let's say, more connection needed here. I will bring more leads. So on my tracks, now I will be removing the previous cables for my short circuit. I will first do what we call it delta preparation. So I have this little jumpers helping me. Just like channel 2, sorry, black of channel 1 connected to red of channel 2, black of channel 2 connected to red of channel 3, and last black of channel 3 connected to the red of channel 1. So I have like phase 1, 2, 3, but there is a delta loop in the picture. I will be using this as a second and this as a third, sorry, as a first connection for phase UV that one I will apply at, and at the same time I will measure using my Kelvin lead, which is having the same output from this side. And this time I will be using a thermic lamp. So I can make a three-phase connection. I have another extra clamp. It's not Kelvin, it's normal, just one banana from one side, clamp from the other side. I will need to apply just like the first phase only, UV. I'll be using the third one on the W. And on my drives, I'll be connecting this to the last phase. So on the screen, you can see I made this connection. I know it takes time, but we have verified it. I can click OK, and I can run my test. So I run it on the first phase. I have like 50% on the second phase, 50% on third phase. And I have 100% with the same voltage I apply on the first phase. I will now start switching the cables to make the next connection. I will start from the test setup. I will be just likely doing full shifting. So I will apply it from here, and I will measure across the three phases because this is Kelvin, it has two wires. One will be to put the voltage, and one will be measuring the voltage. Same thing here, but from this phase, I'm only measuring the voltage. So going to tracks now, I would be switching the leads. I would just make a loop. I would be shifting each one like one go down, and when you're at the end, you go up. And I will click run again. So now we apply on the second phase, we measure on the three phases together. So we still have 50-50 on the sides. We'll now start switching on the power transformer for the last phase. So I will go between W and U, and the remaining will be only measuring the voltage. On my tracks again, I will be making another loop. So I will take this, I'll make it a little bit one step down. So now I have the full connection. I will click play on my track screen. So I expect also to have the same result as first phase. So I have 50-50 on all while apply 100 on each phase. Which is considered maybe a good result for this type of transformer. This is also, you can make sure that you have run demagnetization before this test, and this is to prove it. Of course, this is only to provide you the way we are doing it using the facts, and we are happy with this result. We will be saving it. I will go to the test report, and we can see now the magnetic balance test result are added. I can just hide this red box. So I have now the full result also copied. So this is one full report showing all the three tests together. I can later export it or save it in a USB stick and take it with me for more investigation if it's needed, or just to report it so I can later refer to it. Now what we show here is a three test. If I can go to application, we could show short circuit, frequency response of stray losses, magnetic balance test, and around 26 minutes we spent with you. And if you have any questions, you can refer back to me, Jafar Al-Jurazi from Mega Bahrain office. Thank you for being with us.
Days ago, I was doing lots of testing with you, and now we will have your questions. So if you have any questions, you can please start sharing these through the Q session. And if you like to send me also some of your questions, if you just scan the QR code, this will take you by the mobile camera to my contact details. And you can just forward me through email or texting over WhatsApp. So any questions so far we have, Sausan, or it's well delivered?
Assalamu alaikum.
Yes, wa alaikum salam.
Yes, it is needed to measure short circuit impedance for all position, for tab position on the tab 1, on tab 3, or like this, different tab position.
Thank you for the question. Yes, you need to test, I would say the best is the highest tab, which is including all the terms, which is the purpose of the test to see if there is an issue. It will be seen if you test the highest voltage tab, or even lowest if you have reverse turns tab changer connection. So either highest or lowest, or it is the idea to test and find deformation for short circuit winding. And by testing from that point, you can find the issue. It is not necessarily to test all tabs.
Uh, but I don't have reference value on the main plate of transformer for the highest and the lowest, only one short circuit impedance.
Yes, that's what the factory nominally usually doing. They do it only at one tab and they record it. This is based on the specification, usually the client for this power transformer asking. But you can make it today as a reference to be used in the future. I mean, to test and keep it as a result for the future to compare. Or maybe you do it only at the nominal. If you do it with the highest tab, there will be some percentage increased, of course, due to the extra copper and connection as well. So
Yes.
you can take the two way of doing it, either to continue doing it from the nominal, which is something just because somebody before have done it only on the nominal and comparing. But if you start having issues on only little turns that within the tabs, the extra turns, then you might do it for the full turns, which is the highest tab, and then you could see more.
This is a routine test. Test is important for every maintenance.
Uh, it is
Yeah,
not
it is
taking.
important for field.
I know what you mean. If you look
Yes.
clearly to the standard, it is not mentioned it is a routine test.
It is not
Uh,
like
yes.
widening resistance, measure resistance DC like this.
Yeah, that one is a routine test, and it is very, very good test that everybody is doing. But if you don't really spend a huge time to have more tests to be added to your list, like this short circuit or FRSL, it would be good as well. The more data you collect from your power transformer would be good. This is usually factory acceptance test. Once it's performed, nobody do it at the field. Actually, due to some difficulty that in the past it is needed for a high voltage, like 380 volts or 415 three-phase source to be connected to power transformer, which consume lots of energy, and then you can get the result. What today we offer with the trucks, you use, as I said, a very, very small power, very little current to get this result. It's a very clever if you can do and find the final value you are looking for with less efforts. So why not doing it? The
Okay, but
question.
but for a standard IEC, it is not a routine test for field test.
Yeah, but
Yes.
these standards keep updating itself.
Yes, yes.
It's very slow to update a standard, but today technology is moving much faster than updating the standards. I can mention many cases, like even FRSL, there is no much information about, uh, because mainly the difficulty of doing it was not easily to find in the market. Today, there is many people doing it because they have like affordable equipment, they can do it easily. Even today, the on-load tab changer, we have more knowledge about, more way of testing it. It does save time, it does save cost on us. So if you look to the standard, it's have a lag before, I mean, updating it with what today people can do in reality as a testing on.
I understand
I'm
you
now
mean.
arguing the standard that they are very slow to update, but of course they are going to do. And there will be more knowledge about the way of testing. We have different committee. We have CGRE, we have IEC, we have IEEE, and we have also some local country standards, which they are also building their own. This takes time until we see it really polished in a nice standards, clearly pushing in several directions.
Yes, yes. What is the main objective of the short circuit impedance? ED current and hysteresis losses only,
For the short circuit, we don't talk about eddy current. We talk mainly about deformation because we have only one frequency. I would like
yes,
push your question toward FRSL, where we add the frequency with the short circuit, and then we start seeing issue related to the eddy
ah,
current.
when
Or,
we change the frequency, we already measure. It is important for ED current and the hysteresis losses. Okay, agree with me?
yeah,
I,
we say we test so we can find issue related to the eddy current.
mm.
This I agree with you.
But for short circuit, without a change in frequency, it is what is the meaning of this test here? The main objective of
If I
this?
can give you the full picture, short circuit is only a test run at 50 hertz or 60 hertz only. We
Oh,
don't
yes.
change the frequency. FRSL, it's exactly the same, but we change the frequency and we look for the resistance versus the frequency.
Mm.
So in this test, we could see the resistance at 500 hertz or 400 hertz, which can be differ. And this is what we can indicate from that this power transformer start having more ED losses.
Yes, for high frequency.
Yes,
It is a
and
high
this
frequency.
usually for the higher power transformers where they have strands, and these strands might be getting shorts due to very low insulation they use, or maybe due to some years of operation that you start losing the insulation between the strands, and then you will have more path for the current at higher frequency, which is what I explain as a skin effect. It's even can pass from one strand to another, I mean, between the conductors itself.
Okay. I need now to understand what is the difference between widening resistance and short circuit resistance. This is the measure. I see some interference between these two type of tests.
For winding resistance, we are doing it at 0 hertz, which is DC. For
Yes.
short circuit, we are putting 50 hertz, which is an AC. I show in one graph that you have increase of the resistance as long as you increase the frequency, which is normal phenomena for the skin effect. The more frequency you have, the higher resistance you will measure.
Yes. What there is another question, if you can answer it. What is
Yes,
the meaning of dynamic resistance?
dynamic is like combining time with your resistor, like you make a resistor measurement versus time. And this dynamic only can be applicable where we have change of the resistance during the change of the tap changer. Today, we are not focusing on this. I have done before some dynamic analysis on the on-load tap changer and the way we connect. We can send you this webinar link where you can see it. I
Yes.
spoke in details what do we mean by dynamic resistance,
Mm.
and also I combine it with the dynamic current. There is a big difference when you say I want to measure the current dynamically and I want to measure the resistance dynamically.
Yes. Thank you for you.
Thank you for all
So
the questions. It is nice from you. I see no more questions. I would like to really thanks Ashraf who was with me interacting. Very big thanks to him. And for time being, our webinar being concluded. And if there's no more questions, yes, you can just share it with me. I still have my, I think there is one more question from Ashraf. No? Okay. Then thanks all. And this is my contact details. If you just scan it, I will be with you on your mobile. You can save it and you can share with me all the questions, and I will be glad to answer it for you.
Also, let me remind you there is a small survey in the end of this webinar. So please take some time to fill it up, and you can, through that, you can request a demo or you can request a quotation or just like directly speak to us. Okay? Thank you, everyone, and see you next time.